So, we are discussing the analysis of normal shocks and going through the details of how to gather all information about flow variables downstream of the normal shock. And the last class we had discussed about getting to the Prandtl's relation for normal shocks, that is using the conservation equations. This is something that was done the previous class, so I will quickly go through this. And the conservation equation of mass, momentum, energy for one dimension is used to analyze the normal shock. It is an adiabatic process without any work done. So, you can apply these equations along with the equation of state and a relation for the enthalpy. By using all three equations together, we come to a relation m1 star m2 star equal to 1. This is for this is called the Prandtl's relation, and using this we can convert the equations so that we can exclusively get the equation for downstream Mach number m2 square in terms of m1 square and gamma. And similarly, using the continuity, once we had done this, we can get the equation for the density ratio rho 2 by rho 1 in terms of only Mach number and gamma. So, this is something that will come up again and again. So, now we are left with the pressure ratios, temperature ratios. Let us see how to get to them. Okay. So, here we take the momentum equation again, P2 P1 plus rho 1 U1 square is equal to P2 plus rho 2 U2 square, and do the subtraction, the sort of moving the variables from here to the side is rho 1 U1 square. Now, once we have the Prandtl's relation, that is relating U1 U2 is equal to A star square for conditions across the normal shock, our intention in further analysis would be to try to use this formulation, Prandtl's relation, in order to get to the other flow variables. So, here you get U2 by U1, so this quantity is there. Now, you can divide this by P1, which is done over here, and you can get rho 1 U1 square by P1 multiplied by 1 minus U2 by U1. Now, immediately some things that again come again and again in gas dynamics is the combination P by rho. If you come across this combination P by rho, and it can be converted to the speed of sound for a perfect gas by multiplying and dividing by a gamma. So, if you do that, then you get this term, which is a group of terms, which is gamma P by rho. So, this term comes out to be gamma U1 square by A1 square multiplied by 1 minus U2 by U1. Okay. Now, we will go ahead and see this is m1 square. So, this is gamma m1 square 1 minus U2 by U1. Now, U2 by U1 from the previous analysis, we found what is rho 2 by rho 1, that is U1 by U2. So, U2 by U1 is nothing but rho 1 by rho 2, which is 2 plus gamma minus 1 multiplied by m1 square divided by gamma plus 1 m1 square. So, we just have to import that into this formulation, and what we get here then is 1 minus 2 plus gamma minus 1 m1 square divided by gamma plus 1 m1 square. So that is what you get over here. So this can be simplified here. So you get gamma plus 1 m1 square minus 2 plus gamma minus 1 m1 square, the whole divided by gamma plus 1 m1 square, and we have a gamma m1 square that is over here. And if you do the algebraic manipulations on this, you get P2 by P1 to be equal to 1 plus 2 gamma by gamma minus 1 gamma plus 1 multiplied by m1 square minus 1. So this is now straight forward here. So this is the equation to relate P2 by P1. So we have used the momentum equation as well as the conditions that we just derived here, that is rho 2 by rho 1 is u1 by u2 from the mass conservation. All of them are always, they will have their roots towards the Prandtl's relation u1 u2 is equal to a star square. Now once you get the pressure ratio, then getting temperature ratio is nothing but using the ideal gas equation of state. So P is equal to rho RT. T2 by T1 is P2 by P1 multiplied by rho 1 by rho 2. Now P2 by P1 we have the expression for this, rho 1 by rho 2 we have the expression, and so we can multiply the two expressions, 1 plus 2 gamma by gamma plus 1 m1 square minus 1 multiplied to 2 plus gamma minus 1 m1 square divided by gamma plus 1 m1 square. So this is the final expression for T2 by T1. Now if you observe, you again observe this F2 is only function of gamma and Mach number, that is Mach number. Then you got rho 2 by rho 1, density ratio is function of only gamma and Mach number, and pressure ratio is function of only gamma and Mach number. So this sort of emphasizes that for a normal shock, if you know the upstream conditions, then you can completely determine the downstream conditions. So from here these relate the static quantities across the normal shock. How can stagnation quantities be related across the normal shock? So if we look at the normal shock, it is an adiabatic process, so there is no heat transfer or work done. That means across the normal shock, the total enthalpy H plus B1, H1 plus B1 square by 2 is equal to H2 plus B2 square by 2. Total enthalpy H naught remains a constant. Okay, so that means T naught for a calorically perfect gas, T naught does not change, T naught is a constant. Okay, this is a very important idea, that T naught remains constant across a normal shock. This is for a standing normal shock, stationary normal shock in a supersonic flow. This is what we are analyzing. Now let us go and look at is there any entropy change across the normal shock. So we began our analysis by saying that it is an adiabatic process, but never said that it is a reversible adiabatic process, and reasons are that shock waves generate entropy. This is because within the shock wave, within that small very infinitesimal thickness of shock wave, the transport process become very important, and they give rise to entropy, and high gradients across the shock give rise to the entropy. And entropy change across the shock is, you use the relation now, you know, Cp log T2 by T1 minus R log P2 by P1. Both T2 by T1 and P2 by P1 are determined in the previous analysis. So we substitute for them in terms of T2 by T1 and P2 by P1. And so this expression, once you know these values, you can directly determine the entropy change across the shock wave. Now one should notice that the conservation equations, if you take rho 1 u1 equal to rho 2 u2, p1 plus rho 1 u1 square equal to p2 plus rho 2 u2 square, and h1 plus u1 square by 2 is equal to h2 plus u2 square by 2, just relate the balance of mass, momentum and energy across a discontinuity. And we are doing control volume analysis for the states before the shock and after the shock. So this is the shock, but by this just by these three equations one can not determine what should be the conditions across the shock. Can there be conditions that velocity suddenly increases across the shock? Okay, that kind of a shock can be called as an expansion shock, because the normal shock, whatever we are discussing, is a compression shock. It compresses the gas, increases the pressure and density. Now we can ask the question that is it possible that there is a shock which will suddenly increase the velocity, reduce pressure and density and temperature? Can there be such a solution? And if you look at only the conservation laws, they do not tell you what are the conditions whether such solutions can exist or they cannot exist. And for this you need to bring in the second law of thermodynamics and the entropy considerations. And now we have the relations for entropy, and now that we know this is an adiabatic process, then clearly the change in entropy should always be positive. There are irreversibilities in the system, that means change in entropy will be greater than 0. If you apply this condition to this expression and try to find out what is the condition, since now this expression is only function of gamma and Mach number, so that is upstream Mach number, you will get that m1 has to be greater than 1. So even from entropy considerations, you will find that always shocks exist in supersonic flows. And second thing is that the expansion shock is not permitted because it reduces entropy. It is not possible that you can have a sudden increase in Mach number. So you cannot increase Mach number by a discontinuous jump. So because of these conditions, these entropy considerations, so expansion shock is not possible, only compression shock is possible, and normal shock is a compression shock. Now we know that stagnation temperature across the shock is constant by the virtue of the process being adiabatic, but what about stagnation pressure? So stagnation pressure across the shock, how can we relate this? For this again we go to the entropy relations. Okay, so the entropy relations for across the shock we just discussed is Cp log T2 by T1 minus R log P2 by P1. Now we come to a specific application of the stagnation conditions. Now we know that every point in the flow, so if I take this is normal shock, there is a point before and after the normal shock, and P1 T1 represent the static quantities, and P2 T2 represent static quantities downstream of the shock. Then there is an equivalent point where the entropy remains through an isentropic process. You can take this to P0 and T0. These are equivalent conditions, P0 and T0. So their entropy at P1 T1 and P0 T0 are the same. Similarly, entropy at P2 T2 and P0 2 T0 2 are the same, P01 and T01. So the same equation, that is so change in entropy can be written in terms of changes to the stagnation quantities, and we know that across the shock wave the stagnation temperature does not change, stagnation enthalpy is constant. So T02 by T01 is 1, so this term goes to 0. So you can get the relation telling the change of stagnation pressure. So stagnation pressure ratio P02 by P01 is directly given by, this is delta S. Now delta S at the stagnation conditions is the same as delta S at static conditions, because they are related by an isentropic, each state is related by an isentropic process. So what we find here is that P02 by P01, you can take the inverse logarithm of this process is E minus delta S by R. Now just now we had discussed that the entropy always increases across a normal shock. So delta S is always greater than 0. That means this term is greater than 0. That means that this term will be less than 1. So P02 by P01 is less than 1. That means stagnation pressure decreases across the shock. So this is an important sort of expression, that stagnation pressure decreases across shock. So if you now you have determined for both the static and the stagnation conditions across the shock, and you know the relationships between all of them, that is the Mach number M2 decreases across the shock, pressure increases across the shock, density increases across the shock, temperature increases across the shock, but T02, that is total temperature, remains the same. P02 decreases downstream of the shock. So this gives us all the relations. So now let us put them in. We know how these expressions are, and let us plot them and see how they vary over Mach number. You can see that they vary quite rapidly, and because they vary so rapidly, we cannot plot them on a linear scale, and increase in pressure due to increase of shock as the shock Mach number increases is enormous. There is a significant increase in pressure, and this increase in pressure is accompanied by an increase in temperature also. So as Mach number changes, both pressure and temperature increase significantly. While if you look at what happens to density, it is interesting. Initially it increases, but once you reach higher Mach numbers, it sort of saturates. So it does not increase as much as temperature and pressure do. Stagnation temperature remains constant, stagnation pressure on the other hand decreases significantly. So what are the consequences of this? Because there is a significant generation of entropy, presence of shock waves in devices leads to a lot of losses. So it makes it less efficient. So if you consider process of compression, you have isentropic compression, you have shock compression. So shock compression generates entropy. So a lot of the energy is converted to unusable heat energy. So you see that if you consider two states, one achieved by an isentropic process for the same pressure ratio, another for using a shock process, then the temperature achieved in the shock process will be much higher than the one you get by an isentropic process. So shock processes generate a much higher entropy. So looking at how to use these in designs, or how to put them in devices, then always we should look at trying to reduce entropy losses. So significant effort is put in so that the strength of these shocks can be reduced. Of course, when one looks at supersonic flows, shocks are unavoidable, if not in the design conditions, but when the device works even slightly at an off design conditions, you generate lot of shocks. So the idea is to minimize the strength of shock. Strength of shock is mainly determined, as we know, by its Mach number, and sometimes it is also referred to by the pressure ratio. They are synonymous, because once you know the Mach number, you have a fixed pressure ratio, and so strength of shock you can say is by pressure ratio or the Mach number. So as weak a shock as possible is what we would like. So another interesting thing about the downstream Mach number of shock, you see that always you have the Mach number downstream of the normal shock to be subsonic. A normal shock exists only in supersonic flow, so upstream is supersonic, downstream is subsonic. The way M2 behaves is that it decreases, but then similar to the way density sort of saturates by increasing to a value, the Mach number decreases to a value and saturates, and sort of tends to be a constant. So these are how these values occur. There is another interesting thing about shock waves and a comparison with the isentropic compression, that even though shock waves produce lot of entropy, in some cases, in some applications, particularly for aerodynamic testing, when one looks at extremely high velocities that needs to be achieved, this can the stagnation pressures and temperatures required to achieve those high velocity conditions typical to re-entry or very high Mach number flow will become very large. And this is clear to you from the stagnation conditions that we had already discussed, also in the perspective of shock waves. So if you look at it, as the shock numbers increases, the pressure ratios are actually higher and go higher, and temperature ratios also go higher. So in order to achieve such high pressures and temperatures, it is not very easy to do it in an isentropic compression, because isentropic compression cannot increase temperature. When temperature becomes important, enthalpy becomes important. Isentropic compression does not give that high enthalpies. So, shock compression is often used, and they give rise to what are known as shock tube based tunnels, shock tunnels, where shock compression is used to achieve high pressure and temperature. So, in some cases you need the shock waves and you want to use it for specific purposes. Now, similar to the isentropic charts, normal shocks also you get charts, and the way to use the charts and tables is the same whether you use it for isentropic relations or normal shocks, and they are given at the end of textbooks or in the appendices. So, when we look at solving problems, then we will use either these tables or you can use online calculators. So, with that we come to a close on the analysis of getting to downstream conditions of shock given the upstream conditions, and we are able to relate all the different flow parameters. Now, in the next class what we would see is that we come to what are strong shocks and weak shocks. Are there any limiting conditions? We have some indications through the graphs, but let us look at it. And there is another thermodynamic way of representing the shock known as the Hugonio relation, which does not actually include the information on velocity, just the relation between the two thermodynamic states. That is useful in several cases, and further on we look at where this can be applied in supersonic flows, particularly for the pitot. So, that would be in the next class. Thank you.